Assalamu alaikum everyone. Today we have to start this chapter number 11, which is about utilizing experience based principles to confirm the suitability of a process design. Now, in this chapter, we will actually see that how we can actually make some shortcut methodologies to solve any problem, and we will see that how we can actually develop our own heuristics that can be applicable to any process condition or any cost estimation. It can be specific to one process, or it can be more generalized to get the information about all of the process. Okay, so now let us see what we have in today's lecture. Uses of experience based shortcut methods and guidelines. So we will see that how we can actually make the shortcut methods and what are the certain guidelines that we need to follow, and we will see that what are different advantages of having the shortcut methodologies. Number one, checking new process designs. So if you are going to make any new process design and if you want to check the accurateness of the new process design with some quick calculations, then we can use some shortcut methods. Number two, providing equipment size and performance estimates. So we can use some kind of shortcut technologies or the methodologies by using simple equations to get the information on the equipment size, and we can also imagine that what is the performance of any equipment, and we will see in more details. Helping to troubleshoot problems with operating system. So for the operational processes, if there is any problem within the system, then we can use shortcut methodologies to analyze the problem and to suggest a quick outcome or a quick solution to that problem. Verifying the reasonableness of results of computer calculations and simulations. And if we have some kind of shortcut methodologies in our mind, then we can rely or validate the results that we get from the computer calculations or the simulations to see if there is any problem or error in the system. Number five, providing reasonable initial values for the input to process simulator required to achieve process program convergence. And now this part is more related with the process simulator, and you know that when you run any simulator, then you have to provide the initial estimates to the process streams or for the equipment to, so you can get the final answer from that simulator. So what could be the starting point? We have to initially propose some of the inputs that is required by the simulator, so you can get some reasonable result from that simulator. Now what should be the input value? You have to get those values from the experience. Okay. Number six, obtaining approximate cost for the process units, and then also you can use some cost estimation techniques, and there could be some heuristics to estimate the cost of any process or the utility by simply looking at the flow rates or the simple data that we have in the literature. Okay, so we'll say that what could be the direct estimate or the equations that we can use to get the values for the cost and to analyze the process economics. Number seven, developing preliminary process layout. It can also help you in developing the preliminary layout and how different equipments can be integrated with one another, and what could be the input and output structure of the process, and what could be the input value of a certain equipment, what could be the output value from the certain equipment from the reactor, and then how you can connect that equipment with other equipments. So these are some of the things that we need to consider when we are making the shortcut methodologies. And then characteristics of the heuristics. Now there are four characteristics of the heuristics. A heuristics does not guarantee a solution. Now whenever you are using the heuristics, we have studied the heuristics in chapter number 12. We have seen separators and reactors in terms of temperature and the pressure condition, and we saw that what is the justifications we can provide for the certain equipment, and then what could be the energy penalties. Okay, so a heuristic does not guarantee a solution. It can just give you an idea to solve or to get near to the solution, but it will not give you the real values of some problem. It may contradict with the other heuristics. So because heuristics, it is specific to one problem or one system. So for one system, your developed heuristics may work, but considering the other system, it may not work. Okay, so it is something that is specific to the problem. Number three, it can reduce the time to solve the problem. Okay, so whenever you're designing something or you're trying to solve any problem, or when you go to the industry, you would see the shortcut methods or the heuristic to just quickly get the values for the certain problem, and then you can quickly suggest some solution. Okay, so there we have to use the shortcut methodologies a lot. Okay, its acceptance depend on the immediate context instead of an absolute standard. Okay, so whatever values we get from the heuristics, it is more relevant to the context or the problem that is there, but it will not give you the standard solution for any process. For the standard values or the actual values, you have to use all the relevant chemical engineering equations step by step to get the real value for any problem or to solve any numerical. Okay, the role of experience in the design process. Now, what should be the role of experience in the design process? It is important to be able to apply knowledge gained through experience to future problems. Now, here comes the value of the experience, that whatever things that you learned with your experience, and how you can directly apply those that experience to solve the future problems. It can be the direct understanding of any process, and you can suggest direct solution, or you can use some shortcut methods, or then if you are provided with a set of equations, then you can use those sets of equations one by one to get the actual value for the problem. So it depends on the knowledge from where you start and where you end. Okay, now what is a heuristic? Technical heuristics and shortcut methods. A heuristic is a statement concerning equipment size, operating condition, and equipment performance that reduces the need for calculation. Now, most of the time, and the heuristics are used to estimate the size of the equipment. Sometimes it is used to analyze the operating conditions and the equipment performance. For example, if you're using some kind of reactor or the distillation column, you can use some shortcut methods to analyze what could be the output value, what could be the temperature, pressure, and what is the relationship between the temperature, pressure, and the conversion of feedstock into the product. Okay, so these are some of the things in terms of equipment size, operating conditions, and equipment performance that you can get from using simple heuristics, and that would reduce your calculations, and you can get the quick solution for any problem. Now, maximizing the benefits obtained from the experience. An experienced engineer retains a body of information made up largely of heuristics and shortcut calculation methods that is available to solve new problems. Now, what is the role of the experienced engineer? He cannot just remember all the equations that we studied during the engineering, but he relies more on the heuristics and the shortcut calculation methods that are available in the industries or in the vendors office. Okay, so they can directly use those heuristics and the calculation methods to quickly solve the problem. Obviously, for the initial design and to get the reliability of the process, the first stage is to develop something using the heuristics, and then you can make some detailed design to get the actual values of that process. Okay, now let us see what is this process here, the PAR process. This is basically an approach in which we can use prediction, authentication, and re-evaluation methodology step by step to solve any system. The process by which an engineer uses information and create new heuristics consists of three steps. Now, there are three steps through which you can develop your heuristics or develop your shortcut methods. What are those step-by-step approaches? First one, you have to predict something, then you have to authenticate your prediction, and then you have to reevaluate what you product based on the results that you get from the authentication. So this is a cyclic process, and you keep on doing this circle, and then until and unless you reach a very good shortcut method or very good shortcut equation to reasonably predict the results for any problem in the future. Okay, so let's see these three steps in detail one by one. So part process to maximize benefits of experience, predict, authenticate, and reevaluate. Now what is the prediction here? This is a precondition of the part process. It represents your best prediction of the solution. It often involves making assumptions and applying heuristics based on experience. Now here what you can do, you have to best predict what would be the solution, and then you have to make appropriate assumptions, and then you can use some heuristics to get the result of your assumptions or the predictions. Calculations should be limited to backup of the envelope or shortcut technique. Then you can perform some calculation to get some quick analysis or to get some quick results. Okay, so here you have to just predict what could be the initial value, and what how you can actually solve the system, and what are your assumptions, and which particular equation or heuristic you can use. Then authenticate and analyze. In this step, you seek out equations and relationships. Now here, to know the reliability of your prediction, you have to use some equations and the relationships. And that could be shortcut methods, or that could be dependent on the knowledge that we learned throughout our engineering. Okay, so we have to use some equations and relationships. Do research related to the problem, or if it is some specific problem, then you have to do some research in detail to that specific problem and perform the calculations that lead to its solution. And then you have to use these equations to get some reasonable solution. The ability to carry out this activity provides a necessary but not sufficient condition to be an engineer. Now, if you are having some kind of shortcut methodologies, then it is not necessary that you can be an engineer. But some operator, you can teach some equation to an operator to get some quick values, and then without having any detailed knowledge of the engineering, he can just put the values from the process, and then he can get some like the new value, and see if there is any problem into the system or not, and then how he can actually solve the problem. When possible, information from actual operations is included in order to achieve the best results. Okay, so sometimes the theoretical knowledge, it is different from what we get in the industries. Okay, sometimes we like if we are studying the distillation column, we are relying more on the equations. Okay, that equations actually they represent 95% of the system maybe. Okay, but for getting the actual values from the process, that is the best way. Okay, so we can develop our heuristics depending on the actual values from the process, and then we develop our own equations that can quickly solve any system, or they can predict if there is any fault in the system. Okay, now third one, reevaluate and rethink. The best possible solution from step 2 is compared with the predicted solution in the step 1. Now here in the step 2 we are using some equations to get some reasonable estimate of our calculation, or what according to our aim, and then we compare the results with what we have predicted in the first step. And this is what we will reevaluate and rethink. We will use if there is some like discrepancy in the results that we get from the authentication or the analyzing step, or that if the difference is large to what we have predicted in the first place, then we have to just change or modify the equations, and we have to develop the new heuristics until and unless we get near to what we have predicted in the first part. Okay, when the prediction is not acceptable, it is necessary to correct reasoning that led to the poor prediction. Now, if we are getting some wrong answer for any prediction from the step number 2, then we have to reconsider. Either we can change our assumptions, or we have to see what is a reason that will lead to the poor prediction. It becomes necessary to remove, revise, and replace assumptions made in step 1. This is critical step in learning from experience. Now, if you are getting some different values for this from the step 2 to what you have predicted in step 1, then you have to obviously revise your assumption, and you have to redo the calculation until and unless you reach to the value to what you have actually predicted in the first part. Okay, now this is basically relying, like making assumptions. It is more relevant to what experience you have. Okay, so we will see some examples that what could be the assumptions, and then how you can evaluate, and then how you can think and change the assumptions again depending on each of the process. Okay, so let us solve this example, which is very good, and which we will use the par process, and we will see that how we can actually develop some heuristics or the shortcut methods to solve any problem related to heat transfer. Okay, so let us read this problem statement. Evaluate the heat transfer coefficient for water at 93 degrees centigrade flowing at 3.05 meter per second inside a 38 millimeter tube diameter. From previous experience, you know that the heat transfer coefficient for water at 21 degree centigrade and 1.83 meter per second in these tubes is 5250 watt per meter square centigrade. Follow the part process to establish the heat transfer coefficient at the new conditions. Okay, now these are the new conditions at 3.05 meter per second, and the temperature is 93 degrees centigrade, on which we have to analyze, or on which we have to calculate the heat transfer coefficient. Okay, and the data what we have earlier, we have the information at 21 degree centigrade and 1.83 meter per second, and the heat transfer coefficient at these conditions is, it is 5250 watt per meter square centigrade. Now we have to use this par approach to establish the heat transfer coefficient relation that would be more generalized to this problem, and that could actually predict the correct values of the heat transfer coefficient for any change in temperature if we are using the water. Okay, so let us see how we can actually solve this system here. Now the step number one, we have to make some assumptions here. Now what could be the assumptions for this particular problem? Assume that velocity and temperature have no effect. Now the first assumption that we can make from our experience, that the heat transfer coefficient, it is not dependent on velocity and temperature. Without doing any calculation, it is just our assumption based on our experience. Predicted heat transfer coefficient would be 5250 watt per meter square degree centigrade. Now this is the heat transfer coefficient that we have already for the water at the given conditions. Now how we can analyze this problem? We have made these assumptions, these two assumptions, and then we will authenticate or analyze the problem. Now what we are gonna do here, using the properties given below, we will find that Reynolds number for the water in the tube is by this one. So we will use the Reynolds number equation that we use in the fluid mechanics to estimate the type of flow. Okay, so you have the value for the viscosity, density, diameter of the pipe, and the velocity, and this is viscosity. So you can put all of these values in this equation, and the value that you get here, it is for the turbulent flow. Okay, so you have the value for the turbulent flow. Now if you have studied the heat transfer course, then we have used the equation Cedar-Tate equation to get the value for the Nusselt number, or to get the value for the heat transfer coefficient. Now what is this heat transfer coefficient here? It basically represents the Nusselt number, that is equal to H, which is the heat transfer coefficient, D is the diameter of the pipeline, and K is the thermal conductivity. Now we have this equation, and we get this equation is called as the Cedar-Tate equation, that is equal to 0.023. Then we have this factor rho ut by mu, which is the Reynolds number, and then we can have this equation Cp mu by K, which is basically representing you the Prandtl number. Okay, now we can use different kinds of dimensionless number. We have like Nusselt number in this equation, we have a Reynolds number in this equation, and then we can have the Prandtl number in this equation. So we are like we are relying more on the dimensionless numbers to get the value for the heat transfer coefficient. Okay, so we will use this heat transfer coefficient equation, which is the Cedar-Tate equation, that can be used if the value for the Reynolds number is greater than 10,000. Okay, so the value for the Reynolds Now the value for the Reynolds number is already greater than 10,000, so we can use this Cedar rate equation to get the value for the heat transfer coefficient. Now what we have here from the book, we have this data already. So we have properties here, and then we have the temperature here. Now we can get the value for the density at 21 degrees centigrade. Similarly, we can have the value for the density at 93. We can have the value for the heat transfer. This one is sorry, thermal conductivity at these two temperatures. We have the value for the Cp at these two temperatures, and then we have the value for the viscosity at these two temperatures. Now this is the information that is already provided to us, and what we actually do here, we will take the ratio here, the ratio of the new one and the old one. So this is the new one and this is the old one. So we will simply calculate the ratio here, and we will see that how we can actually use this ratio in our analysis. Now what you can do here, you can go back here in equation 11.1 and you can rearrange this equation in the form of heat transfer coefficient H. Okay, so you can bring the D here on the right hand side, you can divide it here, and similarly you can multiply the K here in the right hand side, and you can simplify the equation in terms of H. Okay, so H represents you the heat transfer coefficient at 21 degrees centigrade. Now what we are gonna do here, this H basically, as I told you, we can rearrange the equation to get the values in terms of H, and then we can have the value H dash, which is basically the heat transfer coefficient at the new values. The new value, what is the new value? At 93 degrees centigrade. So what we are gonna do here, we can have the equation in terms of H. So you have already rearranged this equation, and then you can divide this H with the new H dash, okay, to get the new value for the heat transfer coefficient. So you can get the equation in terms of d by d dash. Dash is missing here, so you can have d by d dash. Then you can have u dash by u, rho dash by rho, mu by mu dash, cp dash by cp, k dash by k. Okay, so here you would see that for some of these properties like velocity, density, cp, you can see the dash in the numerator. However, here for the viscosity and this one, the diameter, you would get the value d dash in the denominator. So you can get this kind of arrangement when you can simplify this equation, when you can write down this equation in terms of h, and then you can divide this equation with h dash. Okay, the same equation. Okay, so you can have this kind of relationship, and when you put the values for the diameter, for the velocity, density, the new value, the old value and the new value. Similarly here for the Cp and K dash, you can have this equation and you can solve this equation. The value for the for this heat transfer coefficient ratio, it would be equal to 2.725. Now here you have already the value for the H, which is 5250. So you can multiply this 5250 with this one value, and you can have the value for the new heat transfer coefficient, which comes out to be 14,300 watt per meter square second. Now what we see here actually, what is our main aim here by doing this kind of analysis, the initial assumption that velocity and temperature do not have significant effect is incorrect. Now the first assumption that we made here, the velocity and temperature have no effect on the heat transfer coefficient. Now this assumption is wrong. Why? If you compare these values here, like for the velocity, you can see the value here. If you are making the ratio here and solve this one, so the value it will be equal to 1.50, which is greater than 1, very much greater than 1. So the heat transfer coefficient, it has it can be affected by the velocity. Okay, so it can so that's why our assumption is wrong. So the heat transfer coefficient is depending on the velocity. However, in terms of diameter, you can get the value 1. The same is the case with 0.973. It is close to 1, which is density, and the same is the case with the Cp here, Cp, and similarly the this one, thermal conductivity. So the values that are closer to 1, they have the minimum effect on the heat transfer coefficient, and the values they have the values greater than 1, like this one velocity and this viscosity, they have more dependency on this heat transfer coefficient, or the heat transfer coefficient is more dependent on these two things that we are actually ignoring in our assumptions. Okay, so we get the value for this new heat transfer coefficient here. So the initial assumption that the velocity and temperature do not have significant effect is incorrect. Equation 11.3 reveals the velocity effect of a factor 1.5 and viscosity effect of factor 1.73. All other factors are close to 1. So the main factors that are contributing towards the heat transfer coefficient, it is the velocity and it is the viscosity. Okay, now going into slightly more details, we have to reevaluate and rethink about this analysis. The original assumptions that velocity and temperature had no effect on the heat transfer coefficient have been rejected. Improved assumptions for the future predictions are: now the new assumptions that we can make from this analysis, the temperature and effect on viscosity must be evaluated. Now there is some effect between the temperature and the viscosity. So we know that from the fluid mechanics, the temperature and viscosity, there is always some effect in terms of gases and liquids and oils also. We know that one. So we have to see the details and the relationship between the temperature and the viscosity for the given problem. Then the effects of temperature on Cp, density, and K are negligible. The effect of this one, Cp, specific heat, density, and K are negligible. So we see this value from here. The density and this Cp and K, so they have the least effect on the temperature or on the heat transfer coefficient. Pipe diameter has a small effect on H. So we know that we are not changing any diameter, but if we can change, maybe it will be having very less effect on the system, because we cannot change the diameter of the pipelines a lot in the industries. Okay, the things that actually change, it can be viscosity, it can be thermal conductivity, or this kind of thing. Okay, so most of the time the pipe diameter remains unchanged. Okay, number 4, results are limited to the range when where the CHE425 equation is valid. With these assumptions, the values for water at 21 degrees C are substituted in the equation 11.2. This creates a useful heuristic for evaluating the heat transfer coefficients of water. Now, when you have this kind of analysis, we have got some of the results from the analysis. Now we can revisit our equation to get more modified equation or the more shortcut method to analyze the heat transfer coefficient for the water. Now, by this analysis, what we know here, the heat transfer coefficient, it is depending on the velocity and the viscosity. So from here we can see this one, the ratio between the viscosity, it is new viscosity divided by old viscosity 0.8, and in terms this one is velocity, and in terms of viscosity, you can have old viscosity divided by new viscosity with the power 0.47. So the new equation that we can make here, we can have the velocity factor and we can have the viscosity factor here. Okay, now you have to multiply the velocity. As you can see, this one in the equation, it is being on the numerator if you're writing in terms of new velocity, and here for the viscosity it is in the denominator. So the new equation that we get here, it will be in this form: 125 multiplied by velocity 0.8 divided by viscosity 0.47. Now if you put the values here for the velocity and the viscosity that we have in the equation earlier, like this data, we can put the viscosity and we have the value for the temperature, velocity, sorry, 1.83. So you can get some value which is close to this one. Okay, now for this system, we have actually developed this new shortcut equation that can be used to analyze the heat transfer coefficient and how it can change for the water. Okay, so for any system, if you put the old values or the new values, you would be getting nearly the correct value that we initially estimated from the real equations. Okay, so you can solve this equation and let me know if you don't understand anything. Okay, thank you.